So, okay, so where did we stop? Oh, I just want to go back. So you have two kinds of friction. Yes. Oh, thank you. Oh, thank you, thank you. What's your name? Gabi. It's good. If I remember your name, it's good. Okay. So you have two kinds of friction. You have static friction and then kinetic friction, right? And I want to make sure that, so if you use this app, okay, it's a great app to understand. So you see, first of all, because I have assigned homework about friction, it's for next week, but you see static friction is like a reaction force. You push, it's going to push back. You push harder, it's going to push back harder until you reach a maximum. When you overcome that maximum, it's going to be about 120 here or 121, but 125 Newton, it's going to be the maximum. Then it's going to start to move. I want to bring the attention because it's a typical question on test number 2. You can see that the static friction is always larger than the kinetic friction. And the kinetic friction always stay the same. If you don't change the mass, if you don't change the materials in contact, it's not going to change. You see, it's going to stay the same. Agree? So you saw here that the maximum static friction is about 125 Newton, but the kinetic friction is about 94 Newton. So in this case, the only force acting on the crate is going to be kinetic friction. So the frictional forces always oppose the motion. So they are anti-parallel to the motion. Is that clear? In addition to that, obviously, the friction depends on the material in contact. So for example, you have, I'm not sure what it is here, maybe some kind of grass and wood. So if I want to push it, I don't know, I lost my dummy. So if I want to push it, you see, you're going to have some kind of friction. Now I can decrease the friction here, okay? And so by decreasing the friction, you see the flow here? It's less like less dirt. So the friction is going to decrease and it's going to start early. And you see the kinetic friction now it's much smaller. It's 23. Before it was 94. So first, the friction depends on the material in contact. Second, that's not all. It depends also on how hard the floor is being pushed on. Okay, so now I have increased the mass here. Okay, so the floor is going to be pushed on harder. So the normal force will be larger. Do you agree? So you expect the frictional forces to be larger. And you can see I push. I cannot get them moving. It's too heavy. I cannot even get them moving, right? So conclusion, friction depends on two things. The material in contact here, the materials in contact, but also how hard the surface is being pushed on. I didn't say it depends on the weight because it depends also if there is something lifting the masses. So if you lift the masses, for example, you're going to decrease the force you are pushing on the floor. So it depends on how hard the floor is being pushed on, which means the normal force. As a consequence of that, okay, so the equation will be So for the maximum static friction, so it's the maximum, right? You push and you push back. The maximum will be equals to a coefficient. So that coefficient has to be smaller than 1 and it has no unit and it depends on materials here. So is it, for example, wood on grass? Is it wood on asphalt, for example? All that will be defined, depends on that coefficient, right? Or the coefficient depends on what are the materials in contact. Is that clear? So how do we compute those coefficients? We have to do experiments, right? So it will be engineering times the normal force. So it depends on the materials and how hard the surface is being pushed on. For example, if I put my hand here, right, it's going to be acted upon by a normal force, which is perpendicular. If I don't push very hard, so it's not going to push hard on me, you see, it's going to slide. Do you see how it's sliding? Mm-hmm. But if I push really, really hard, I'm going to increase the friction. And now it doesn't slide at all, right? Because I'm pushing so hard, the normal force is going to be huge. Okay? So it depends on the normal force. Now, the kinetic friction, it has the same expression, but now the coefficient here will be the kinetic coefficient, but it's also times, it's going to be also multiplied, you have to multiply also by the normal force. And the kinetic friction is always smaller than maximum static friction. So in the experiment I did here, you saw that the maximum static friction was about 120 Newton or 120 something, but the kinetic friction was 94. So once something, you try to push something, once it starts moving, it's going to be easier. Right? What it's hard is to get it to move because of static friction. Agree? Okay, so if you have any question, let me know. Okay, so we did that. I don't know where we stopped. Okay, so you see all those coefficients here depends on materials in contact, rubber on concrete. For kinetic, the coefficient is going to be 0.68. For static, it's going to be larger. So that's why static friction is always larger than kinetic, because then the normal force will be the same for both of them. So you always have friction. And friction is a good thing because without static friction, we will not be able to walk, right? You push on the ground is pushing back on you. And we talk about rock climbing, where you want to increase the static friction as much as possible. So that's why you want to make sure that the center of gravity is just above your foot to increase the push on the surface, so to increase the static friction. Okay, so let's do something easy. You see, the only force acting here is kinetic friction. So that will be my free body diagram. Weight is pulling down. It's going to be balanced out by the normal force. Normal means perpendicular. The floor is, or the snow is being pushed down. So it's going to push back up. Right? So that's called the normal force. And then you have kinetic friction. So very easy here. What is the kinetic friction in that case? And you have the coefficient. Okay, so don't wait for me. You are my last class, that's why I'm tired. At 2 p.m. I'm very tired. So don't wait for me. So the free body diagram has been done for you. So each time you see kinetic friction, you're going to write down the equation. And I have to emphasize that here it's only the magnitude involved in this equation. What does that mean? It means there is no negative sign. Okay, components of forces can be negative, but not the magnitude. Remember that? When you have a vector, this is the magnitude here, and then you have components. So components can be negative, but not the magnitude. Magnitude is how much the length here of the arrow. Is that clear? So in magnitude, using the magnitude only, we have the kinetic friction equals the coefficient times the normal force. So that's I want. This I know. So I need to find the normal force. And it's an equilibrium. So how can I find the normal force? Very good. In that case, it's going to be equal to the gravity. What's your name? Daniela. Exactly. You see, equilibrium along the y-axis. You remember, everything along the y is ignoring whatever is happening along the x. So along the y, nothing is happening. It doesn't go to space. It doesn't go inside the earth. So it's in equilibrium. So everything up equals everything down. And this is only using the magnitude if you do it this way. Otherwise, if you use the book, you can say the sum of the y component equals 0. So then in that case, you can have negative. If you use it this way, there is no negative here, just magnitude. So what is up? We only have the normal force. What is down? We only have the weight. So in that case, but it doesn't have to be the case because if I pull in this direction, right? So if I lift a little bit, then the normal force will not be equal to the weight. Remember, we discussed that if you lift something, the weight will be less. So the normal force will be less, the apparent weight. So anyway, so in that case, kinetic friction will be 0.05 times, and then the weight, it's going to be very good, 400. And we suppose that G, because if I take 9.8, it's easier to take 10. So it's going to be in magnitude. Okay, I can put like absolute value, like symbols, so to make sure it's a magnitude. Usually we do that. Okay, so that's to show it's the magnitude equals 20 Newton. Do you agree? Now, if I want to talk about the component, okay, so the x component will be minus 20 Newton because it's a vector and it's pointing to the left. So here it's only involving magnitude. Okay? Agree? Okay. So dealing with the acceleration, what matters is the net force. The acceleration will always be in the same direction as the winner. We can call that a winner, like the net force. Example, she jumped from an airplane and air resistance started to build up. Is there a net force? Yes, there is a winner, and the winner is down. So the acceleration is down. Okay, because the acceleration is in the same direction as the winner, if you want. So there is an acceleration down. Okay, so she's gonna speed up. So what's happening here? Because she's uh, spinning up, the air resistance depends on your speed. Makes sense when you run, for example, on the beach. Faster you go, more air resistance you're gonna encounter, right? If you go really, really fast, the air is gonna push back on you even more. So as she goes faster, because she has an acceleration, air resistance it's gonna increase. So let me ask you something. What's happening? Does she have an acceleration? Is there a winner? Yes. But is the acceleration the same as before? No, it's a smaller acceleration. Is she still spinning up?
Yeah.
Yes, but not at the same rate. Okay, so it's like you lose weight. Okay, the first month you lose 8 pounds. Second month you lose 5 pounds. So you're not. Of course, you are losing. Um, you are losing less, but it's compounding. Okay, you are still losing weight. It's like inflation. They say, oh, this month wonderful, the inflation is only 2%, but last month it was still, you still have inflation, right? So the prices keep increasing. Since like 3 years ago, we are at 20% up, right? So the rate at which it's increasing, it's going to be less, but it's still increasing. So she's still spinning up. Agree? So it's not the acceleration will not be constant. It's compounding. So she's still accelerating. She's still going faster, but at a lower rate. What about here? What's happening here?
Mhm.
Is there an acceleration? No. She is in dynamic equilibrium. The velocity is constant, so the acceleration is 0. And she reached a cruising speed. She reached the terminal speed. So it's not like she's stopping mid-air. No, she's still going down, but at a constant speed. Now, what's happening if all of a sudden she opens the parachute? It doesn't mean that she's gonna go up. That's not true. It means that she's gonna slow down. So the acceleration now is where? Down or up? Up. But because she was still moving, she kept moving, okay, but she's slowing down. And because she's slowing down at some point, you see air resistance is going to match with the weight. Air resistance is going to decrease, matches the weight, and she has a new cruising speed. You have to do that, otherwise you're going to crash on the ground, right? You have to slow your speed as much as possible before you land. So inflation works the same way. It's compounding. Okay, if it say, oh, inflation decreases only 1%, but 1% before that it was 3%, before that it was 5%. So the prices are still increasing, right? Do you agree? I mean, I go to Costco, I see with my eyes. I know how much I pay. So anyway, that's the idea. Okay? So, for example, if you jump from an airplane, you're still going to have some air resistance. Okay? You're not going to be in free fall. So your speed when you're going to land will be about 70 miles per hour, which is still bad, but you might survive. Now, if you open a parachute, it will be about 10 miles per hour. So it's much more gentle, and you won't break a leg. So air resistance also very important, and it depends on the speed. Actually, it depends on the speed square. So if you bike, for example, faster you bike, then the air resistance will increase. It depends on what? What else? What is the special shape of the helmet they have? Do you see the shape?
Mhm.
It's aerodynamics, right? Because you want the air to go and like do something like this, right? So it depends on the surface area. More surface area you're exposed to the air, it will slow you down more. Does it make sense? So someone, like I had a grad student, I think it was 2 years ago, I forgot, and who sent me, if I can find It was an Italian something. Eh, one. I just have so many stuff. I just have to find Newton. Oh, here. It's not what I'm looking for, but here, if you want to increase the workout, they have this crazy thing that you can buy. And of course, you're gonna increase the air resistance, right? Because you increase the surface area. So air resistance depends on the surface area, and it's gonna make it harder for you to run. And that's the idea, right? So you can train. Okay, this is what I'm looking for. Uh, I don't, the sound doesn't matter. You see, less surface area, more, less air resistance. Isn't that awesome? I think after that they changed the rules, right? Because that and you need the muscles to do that. It's not that easy. And I think he's gonna pass the motorcycle. I'm not sure. It's Italian. He's Italian. Michael Guerra. He's so scared, you know. You need to have a lot of balance. Wow. And then you have to catch up, right? It's not that easy. Okay, so you need about friction. You need friction to work, right? So we're going to talk about Newton's third law. For every action, we have a reaction, opposite and equal. Okay, so you cannot push harder than you are being pushed. So when you walk, right, you have static friction. Without that friction, you cannot walk. If it was only ice, I will be like walking at on the same spot. You see, like you see in cartoon. So I push the ground push me, right? So I found this a snake here, and that was not very nice of the picture. See, there was no friction, so it is not going anywhere. It's just going. So there was so little friction that it has such a hard time. So if you have a pet snake, maybe you can try. I don't know. Uh, okay, and then you see, if you want to decrease also the amount of air, what they do, like they have a race and it's a team, right? So they take turn to be behind or in front. So those behind, it will be easier for them to back, right? Because first of all, there is less air density, and also they are not exposed so much to air resistance. And when this guy gets tired, this one take over. And that's how they do it. So if you've seen birds, you know, the goose, the geese flying, you always have a leader, and then the leader goes to the back, and someone else take the spot, right? So it's the same idea. Okay, so static equilibrium, you need to know, you know, which forces are involved. So for example, in that case, you're gonna have a pull, maybe two pull, if you have two strings, right? And then she's not moving. She is in static equilibrium. she's pushing the rock, so the rock is pushing back. So that will be the normal force. Normal means perpendicular. The foot here is not sliding, so it means you have static friction always along the surface. And at the center of mass here, you're going to have the weight straight down. And when you add all those vectors, tail to head, you go back to the same place. It's going to be 0. So everything up, all the components up will be equals to the sum of all the components down in magnitude. All the sum of all the components to the left will be equal to the sum of all the components to the right. Do you agree? Mhm. So you see those special rope for climbing, they need to support a lot of weight. Okay. So which one will make more sense? Do you think this one will have more load or this one? The one with 20 degrees or 120? 120. 20, right? So 20 it means it's going to support more load. Okay, why is that? Because remember, a vector, so here it's a tension, comes into two components. And here it's only the y component doing the lifting. So if you increase the weight down, you need to increase the y component. So that's why they have to come together. So you're going to get more y component. If the load like is a child, okay, you don't need that much lifting. Is that clear? I had a demo and I'm not sure if I remember. So for the test number 2, for example, I have to remember. So you see, if you have two strings like this, vertical, do you agree that each string will carry relative to the weight, half of the weight, if it's vertical, right?
Mhm.
If there is an angle, each tension will have to be more, right? Because there is also an X component. But my point is, so if I go, oh, so I forgot how to do it. So if I go, okay, so this is my string. Do you see, everyone? So if I go all the way, if I go all the way, so all the length here, do you see that the load only lifted half of the string, right? So I'm pulling the whole length, yeah, all length, all length, all length, all length, and the load will move only half the string, right? So that's the price to pay. So anyway, so you want if you go rock climbing, you check what's the maximum weight, right? You want to be careful with that. Okay, let's do um, let's try to know if we know how to draw the forces, right? So let's see. You are pulling mass here, but it's moving at a constant speed. So it's a dynamic equilibrium. Can you draw first? Let's draw first, right? Can you draw all the forces? And remember, everything, all the forces come into components, and each component has a different job. So this is the x-axis here, and this is the y-axis. And if it's moving at a constant velocity, that means the acceleration is 0, which means that everything up in magnitude has to be everything down in magnitude, and we are only talking about components, but the magnitude, and everything to the right equals everything down. Left, sorry. See, I'm tired. 2 p.m. I'm tired. So what are the forces acting on the system?
Gravity.
Gravity. Okay, that's already Good. So 100 Newton, and it's down. What else? Normal force, very good. So the ground is being pushed, right? It's not very happy. So it's going to push back, but there is a lift here. Okay, so it's not going to be exactly the weight. It's going to be less than the weight because it has some help here. What else? The pull, very good, right? So it's a tension. So I'm going to make my tension here. And that's you are not satisfied with this because you want to find, and then yes, someone said something else. Yes, the friction, the kinetic friction, right? If it's moving. Exactly. The kinetic friction. Kinetic friction is opposing the motion. Okay, because you see, otherwise it will accelerate. So you need some kinetic friction. And then the next step, once you have identified all the forces acting on the system, you want to think components. So this one I don't worry, it's along the X. This one I don't worry, it's along the Y. This one I don't worry. Oh, this one I have to worry. Okay? So remember, the tail is attached at the origin, and then the head of the vector is always showing you the components in the XY coordinate system. Okay, so it means it has two components. Okay, it has a Y component here. Okay, so T, Y, and it has a X component. Do you agree?
Mm-hmm.
So remember how it works. Each time you have a vector, you have to attach it, right? So it doesn't fly away. And that point here, you see, it's just algebra. That point here has an X and a Y. Of course, the X will be the X component, the Y will be the Y component, and then you can work in a right angle triangle and find out how can you find the X, how you can find the Y. Are you using cosine? Are you using sine? So if you don't use the polar graph, it's easier, but you know the cosine does not have always to be x, and the sine does not have to be always sine. Forgot what I said, but y doesn't have to be sine, and x doesn't have to be cosine if you are using geometry. Agree? Okay, so now we can walk. So now I'm going to say, I want to find the kinetic friction. So both axes are independent from each other, okay? They mind their own business. They don't care about each other. So along the horizontal, what is the one to the right? Tx, very good. It's Tx. Only the x component of the tension is making the forward motion happening. So Tx, okay, the x component, so that's going to be 170 cosine 30, right? And what is pulling to the left? The kinetic friction. You see, that's not that hard. Okay? So then you take your calculator, 170 cosine 30, 147. Do you agree? Mhm. And now, I don't know, maybe they're gonna ask you, can you find the normal force? Can you try that? Can you find the normal force? So you see the normal force will be less than the weight because you are lifting as well. So along the y-axis, okay, you can say everything up equals everything down in magnitude. Up, you look at so the secret, the recipe is to make a picture, to make a diagram, and on your diagram, you want to have all the components. And then it's easy to see what is pointing up and what is pointing down. So up, you have the normal force plus up, you have the y component. That's why I was so annoying with the vector and the component. Okay, so first you master the math, and then you can do the physics. But you need to know how to find components. So that's gonna be 85. Thank you, thank you, thank you. Okay. So now can you find the coefficient of kinetic friction using the equation? Don't stare, do it. Using the equation. So the equation is kinetic friction equals coefficient times the normal force, right? In magnitude. I insist. That's going to be in magnitude. So that will be 147, and it doesn't work because I pull a problem from my head. So the coefficient is not supposed to be equals to 1, so for larger than 1. So forget about that question. So forget about that question. Okay? So that everything else is right. Okay. Let's say you have this lady here, and I don't know what she's doing. She's pushing the wall. Maybe it's some kind of stretching, or maybe it's push up. Okay, so can you find can you draw at least the forces acting on her? I cannot even see her hands. Oh, how much was it? The normal force was. Is that 85 here? Yeah, right? So no, that there was a mistake here. So it's the normal force, 170 sine 30, okay, equals to 100. So it's going to be 1 minus 170 sine 30. So how much is that? 15 Newton. Okay. And this one doesn't work because I didn't use a realistic problem. Right. Okay, the lady. So what are the forces? And she doesn't slide, right? So what are the forces acting on her? Huh? Gravity, very good. So gravity somewhere here, that's the center of mass, so that gravity. What else? From the floor, what do you have? The normal force, so I'm gonna have n sub 1. What else? She doesn't slide. Static friction. Okay, so static friction will be in this direction, right? So that will be the static friction here. Static friction, so she doesn't slide. And what else? She's pushing the wall for some reason. So the wall is gonna
Push back.
push back. Now, what is pushing to the left? And normal force. So you have the normal force from the wall equals the static friction because it's pushing to the right. And you can do that exercise. You can kind of come up with all kind of demo, right? So if you take a bathroom scale and tape it or place it on the wall and you push a little bit, you're gonna see the reading. And you push harder and you're gonna see the reading even increasing. And at some point you're gonna slide. If you push really, really, really hard, you're gonna reach the static friction, which is maximum. Now you push on the ground, right? So the ground is going to push back on you. So that normal force equals to the weight. Okay? Okay, so here you have different situations. So here it's the same kind of situation. The weight is down, you push on the ground, the normal force is always perpendicular from the surface to the system. You have static friction if you try to slide, okay, so it's going to stop you from sliding. If you're pushing this way, it's going to push back. Normal force here, always perpendicular. What do you think here? Is the sofa accelerating or not accelerating? Yeah, so you have the push, you have kinetic friction, you have the weight and the normal force. So yes,
Yeah.
right? Because the push is larger than the kinetic friction. If you want to find the acceleration, it's going to be winner minus loser equals MA. Okay, we're going to see that next. So this one, is it moving at a constant speed? Yes, because you have the thrust from the engine. You're going to have the air resistance. So they balance out. You have the weight pulling down. And this is like a normal force. It's called the lift. So you push on the air is going to push back on you. It's like if you're in a swimming pool, you have a buoyant force, right? The buoyant force is like a normal force, push up on you. That's why you are lighter. That's why if you go physical therapy, many times they use the pool because you're gonna feel less weight because the buoyant force is pushing up on you, right? So it's like your apparent weight will be less. You feel less heavy. Okay, and this one is a cockroach. I don't know why I put a cockroach. It's a cockroach going. You sweep it out of the window and now it's falling. But because it has a small weight, very quickly it's gonna reach terminal speed, and it's gonna be all right. That's why those animals, they live forever. They never die, and so air resistance here is balanced out by the weight. Okay, let's try to do number one to reinforce, and that's it. The same problem as before. Okay, so you have your x-axis here. You have your y-axis. You do it the same. You have to do it. Okay, if you wait for me to do it, you're not really learning. So you have the weight and what's the mass? 2.5. So the mass is straight down, which is 25 Newton. and then you have the normal force here. Okay, and you have kinetic friction. And it's a dynamic equilibrium, so it's moving at a constant speed. Maybe I should do it a little bit larger. So you see this one has two components. So again, the head here has two components, X component here, and then the Y component. Okay, so along the X-axis, so it's in equilibrium, which means acceleration is zero, the velocity is constant. It's dynamic because it's moving. So what is pulling to the right? The X component, right? So it's gonna be 7, and it's a cosine, right? So if it's in the first quadrant and you are given this angle with the positive x-axis, so then it's always cosine. 6, is that right? 6.6, so 6.6. So it's in equilibrium. So everything to the right equals everything to the left, right? In magnitude, I only take the magnitude. So 6.6 to the right equals the kinetic friction. So it's in magnitude. So the vector will be negative 6.6 Newton. Agree? So that will be the kinetic friction. And then the normal force, you see, along the y-axis, everything up equals everything down. Okay, so I'm waiting. Just write it down. So you look at your diagram. Up you have the y component and the normal force, and down you have the weight, right? So you have the normal force plus, that's going to be 7 and a sine 20, so it's going to be 2.4 equals the weight, which is 25. Is that right? So this is 20 sine 7 sine 20. Okay, so this is 7 cosine 20, and this is 7 sine 20. And that point here has x coordinate and y coordinate. Agree? And the tail is always attached to the origin. Any vector is attached, the tail is at the origin. So the normal force equals 23? Okay, thank you. Newton. No, 22. Thank you. So this is a realistic one. It's a realistic one because I didn't make it in my head. I took it from somewhere. So now we can find the coefficient. So kinetic friction equals the coefficient times the normal force. Okay, this one it will work. The other one I just make it up. So in magnitude, okay, so you are only using the magnitude. So kinetic friction will be 6.6. This is the coefficient, and the normal force is 22.6. So it's going to be 6.6 divided by 22.6, 0.3, right?
Yeah.
Okay. Morality, don't make up things. I'm trying to see maybe 0.3. It's too much. 0.3, 0.3, no. I see here a 0.3 about. That could be static friction. No, that's static friction. 0.3, 0.3 could be polystyrene. No, but that's static. So anyway, you can look it up. Here I have static and kinetic. 0.3. Steel on steel could be 0.3. Metal on wood. Okay, that makes more sense. Like if you have something metallic, like a AC or something like this, that you push on the floor, wooden floor, then the kinetic friction will be 0.3. So those values, there is no equation for it. Okay, you have to do the experiment and try. And they have no unit because it's Newton divided by Newton. Okay? Now you see ice, it's almost zero, obviously. Okay. Okay, and then I'm gonna leave that for the homework. Okay, so for example, this one we already have done it, but now if you introduce friction, if you introduce kinetic friction, what are the forces acting on the man? You have the weight is always straight down. Okay, you have the normal force here, always perpendicular to the surface, and then you have kinetic friction, right? So it could be that it's moving at a constant speed because the x component of the weight is balancing out the kinetic friction. Okay? Okay, so did we do this one? Okay, so if you are at rest or if you are moving in an elevator but a constant speed, that means up equals down. Do you agree? So that means the normal force here will be equals to the weight. So if you are standing on the bathroom scale, that's going to be your real weight. What's going to happen now, when you are you can do an experiment like this. If you go to those big tower, for example, they need powerful elevator. So you are standing on the bathroom scale and then the elevator goes up. It needs to have some acceleration to reach the cruising speed, right? Does that make sense? What's going to happen to the bathroom scale? Do you hit more than your weight, less than your weight, or your weight? More. Very good. And that's going to be the normal force. Okay, whatever it's being pushed is going to push back. So the normal force will be your apparent weight. So now it's all about the system, right? So if I take little Susie, it's little Susie. I don't know if you recognize her, but little Susie in the back. So acceleration is up. So I need a net force up, right? I need a winner up. So that means she has the weight down. And what is up? What is pushing on her up? Normal force. But the normal force has to provide the acceleration, right? So if you are in an elevator like this, right, you want to stay here. So it's pushing on you, right? So to accelerate you. So the normal force, that makes sense, has to be very large here. Okay, so that's why your weight will be more. So we're going to see that your normal force, that will be the winner, minus your weight will be equals to mass times acceleration. If there is an acceleration, that means there is a net force, there is a winner. You can do that as a demo for extra credit, whatever. You go to an elevator and like the big tower, it works best. And you look at the bathroom scale, you read your own weight, but just at the beginning, you should see your weight go up. And it will be the opposite if you go down. Is that clear? So if you are in an elevator now and now it's going down, it's like the bathroom scale is moving away from you. So you're not pushing as hard. So your apparent weight will be less. And if a mean physics professor, all the professors of physics are very mean. If a cut cable here, what's gonna happen? Yeah, of course. Yes, you die. At the end, you're gonna die. But in between, you're gonna be in free fall. Okay, and which means, can you push on the bathroom scale? No. So you're gonna feel weightless. Very good. It doesn't mean that gravity gave up on you, right? It doesn't stop pulling you, but you don't have any support anymore. So the only reason why you feel your own weight is because the ground is pushing on you, right? So for example, if you carry heavy stuff, right, you're gonna feel very heavy. So if there is no support, no normal force, no weight.
So the same effect the astronauts have in the International Space Station.
Yeah, very good, very good. So in the International Space Station, they are constantly falling toward the Earth, but the Earth is curving away. So the astronauts are in free fall, right? And that's a problem because if you do not have any support, your bones will get very weak. The only reason we have strong bone, it's because gravity, right? We are constantly working against gravity. So if we stop working against gravity, our bone, you're gonna have osteoporosis, right? So I feel very bad for those two astronauts stuck for 6 months. So they do have exercise, right? They have way for them to exercise, but still, I'm not sure if it's enough, right? So as you get older, you see how you are losing muscles and you are using bone. And so that's why you have to constantly exercise. Otherwise, you see, when you get very old, you cannot even lift 5 pounds. Forget about 10 pounds, right? So anyway, I feel bad for them. Uh, okay, so that's very interesting. So they have this airplane. It's called zero gravity, but you have to pay for it, right? I think it's still around. So remember projectile motion? So projectile motion, I told you it's free fall, right?
Yeah.
So two things are happening at the same time. It's moving forward at a constant speed, but it's also falling. So he wants to go in a straight line at a constant speed. No, you are falling. I want to go now. No, you are falling. So projectile motion, it's free fall. So that's why they do with this airplane. First, they're gonna take off. So it's like launching a projectile, right? And then they stop the engine. So because they stop the engine, it's gonna follow a projectile motion. But inside, the people will be in free fall. And so it's very cool. So they did this commercial. I think it was for. I just need to be in the right folder. You can do very cool things. So they are waiting to be in free fall, and once they are in free fall, so these guys Okay, so I don't know if it's still on, you have to tell me for next time, but it was called zero gravity for 10 to 15 seconds, which is a lot, but you have to pay. I don't know, it was like $5,000 at the time. I don't know if it's still around. They even at the time they even offered honeymoon in free fall. So if you want something fancy. So any question? Okay, so let's go to the second part, which is about Newton's law. And it's much easier if you pay attention because it's mostly conceptual. Okay, so Newton's, you have three laws of motion. You have the first law, the second law, and the third law. The first law says that if there is no force acting on the system, okay, it will keep going at the same speed forever, or it will be at rest. An object at rest wants to stay at rest. An object in motion wants to stay in motion. And you already saw that with this app, right? So if I remove friction, there is no friction. If I get to, so of course, okay, there is no friction. Okay, so it starts to move, so no friction. Once I let go, no friction, it will keep moving in the same direction at the same speed forever after. So it's a misconception to think that you need a force for something to keep moving. It wants to keep moving, right? And the only reason it's going to stop moving is because of friction, so there is a force acting on it. Otherwise, anything wants to keep moving at the same speed in the same direction. So, for example, inertia. That's why you want a seat belt. So you see, no seat belt, the car is going to stop because there is a force acting on it, right? It's going to push the wall is going to push back. But your body wants to keep going at the same speed in the same direction, and that's how you can damage your neck, right? So that's inertia. The car is stopping, but not your body. Boom. Do you see? It wants to keep moving at the same speed in the same direction unless acted upon, boom, by a force. Wants to keep moving. Ah, oh, that's good. There is something to stop, which is the airbag. So the airbag increases the time of impact, increases the time of impact, so decreases the impact. So remember, put your seatbelt on. Right, I'm going to show you. So what do we call inertia? Inertia is the tendency for an object to stay in motion if it was in motion, or to stay at rest if it was at rest. And how do we measure that? It's going to be the mass. The mass is inertia. So for example, for the same force, it's going to be easier to get something heavy, lighter, with a small mass to move than something with a large mass. So the mass is inertia for motion along a straight line. So for example, if you have an elephant here, of course, it has a very, very, very large inertia. Okay, so if you try to push it, it's going to be very hard. Even if there is no friction, there is more inertia. So to get the same acceleration, you need to apply more force. Okay, so that's called inertia. So for example, if I go back to my little simulation here. No, it's not this one. Did I lost it? I closed it? I closed it. Great. Do you see it? No. Fourth. Okay. Okay, I'm gonna remove the friction. I'm gonna push. I'm gonna push. It still have some inertia, right? Now, if I do, okay, I'm not going to do it this way. I'm gonna remove the friction. Okay, so I'm pushing with a constant speed. Sorry, constant force. Do you see that? So look what's gonna happen if I increase inertia. If I want to get it moving. Okay, so the same force here. have the mass. Okay, that will be the acceleration 1 meter per second per second. Okay? Now, if I increase the mass now, okay, I'm gonna increase the mass. Boom. And here, oh, do you see the acceleration? It's 0.20. Do you see how the acceleration has decreased because it has more inertia? So inertia is the resistance to change the state of motion. And of course, you can even increase even more, and the acceleration went down. I don't know if I can put more weight here. Boom. No, it's either, but it's 0.15, right? So it's even smaller than before for the same force. So here are some demos you can do. So the penny one. So the penny one is very famous. So you have something like a card here, and you have a penny, and if you give a kick, what's gonna happen? The penny is gonna go down in the glass, right? But you have to do it very quick because otherwise it will be static friction involved, which is larger. So if you push it very slowly, it's static friction, so the force is too large and it's going to take the penny with it. But if you do it very quickly, it's going to be kinetic friction. It has inertia. It wants to stay where it was before. Okay, so I don't know if I have a student of mine did something like this, like here. Isn't that cool? So this is inertia. What else? Okay, inertia. Do you see how the leaves stay behind? Do you see that? Right? Because it was not acted upon by a force. The force was only on the trampoline. So the leaves wants to stay where it was. It wants to stay at rest. It doesn't want to move. And then gravity takes over and pulls the leaves down. So that's also inertia. So let me ask you something. Let's see. Here is another idea for a demo. This is hanging from the ceiling, and you have something very heavy here. If you pull very quickly, which string will break? The top or the bottom? Top, you think the top? And if you pull very, very slowly, the top. And the opposite, right? Let's see if I have a demo about it. I don't know what it is here. This one.
In this demonstration, I have two identical heavy
Okay, I need the sound. Can I get the sound? I don't know how to get the sound.
I have two identical heavy balls hanging from two pieces of identical string. Below each ball is another length of string. Now with this first ball, I'm going to quickly pull down on the string. What will happen? Will the top string break or will the bottom
If I
string
ask you
break?
for a pop quiz, which one? Very quick?
Let's find out.
Because
So as you
of
can see, the
inertia.
bottom string broke. This is because the heavy ball has a lot of inertia and it doesn't want to move. When I pulled down quickly on the string, I didn't give the ball enough time to start moving. Now I will pull down on the second ball, but this time I will pull very slowly. The question is, which string will break first, the top string or the bottom string? All right, so we pull slowly. The top string broke this time because I was able to slowly accelerate the ball, get it moving, and I was able to pull the top string.
So you see, an object does not want to move. It does not want to change the state of motion. You need to apply a force, but during enough time for it to decide, okay, if you insist, I'm gonna
apart.
move, but I really don't want to. Okay, so that's called inertia. I saw something about inertia and I forgot what it is. Oh yeah, but no, that's too much to talk about that. Okay. Okay, likewise here, if you have a hammer, you can do the experiment. And if the head is loose, right, you're gonna hit the desk. So the handle will hit the desk, but the head will keep moving at the same speed in the same direction. So it will secure itself on its own on the handle, right? So it's a trick that people who do a lot of work at home, for example, they know. Okay. The tablecloth trick. So likewise, if you do a demo, you want to take a tablecloth, but that's smooth. It has to be smooth, right? You want kinetic friction. And if you pull slowly, okay, you're gonna have static friction and everything will move with it, right? You give enough time, okay, for static friction to work. It's magic. But if you pull very quickly, then you have kinetic friction, and because those objects have inertia, they want to stay where they were. Okay, you all know that trick, right? So let's see.
Go. Go.
Listen, physics is awesome, right? So people are you have to do it very, very quick. And I don't know if you remember that was the buzz on YouTube, right? Okay.
I hate to break that.
There's around the web. Some of them.
In this viral video, rather than a quick flick of the wrist, it's a quick flick of the accelerator. And abracadabra, the tablecloth disappears, and a perfectly laid table remains. But is this turbocharged trick true, or just special effects sorcery?
It's all set up. You ready to ruin Christmas dinner?
I can't wait.
Uncle Jamie always does that. Get started.
There is a trick, okay? It's true they did it, but what they used here underneath that you cannot see, they put like something on the table very, very smooth to decrease the friction, the static friction as much as possible, right? So at the end of the video, I'm not going to show you, but at the end of the video, they do it. I can skip through, so I don't know if I can skip through here.
What this means is that the tablecloth, should, in theory, slip out easy as you please without disturbing anything on the table. That's how I think they did it. This is tablecloth pull, the cheat. 3, 2, 1, go!
They did it. So this is all because of inertia, right? So that's why you want to wear your seatbelt because of you go. Okay, so that idea of inertia was introduced by Galileo. So he said, okay, imagine you have something rolling. So this is supposed to be a ball, and this is supposed to be smooth, and there is no friction. It will go down, and then it wants to go back to the same level it was, right? To make sense, if there is no friction, you go back to the same height. And now you see it's you decrease the slope, so now it's going to be there, right? It's always looking for the same height. What's going to happen in that case? Huh? Yes, very good. Talia. Yes, it will keep moving forever after because it's like it's looking for the same height and sadly it will never find it. right? So it's Galileo who introduced, using a thought experiment, who introduced the concept of inertia, and then Newton build on that. Okay, so for example, if you are speeding up or slowing down, you need a force, right? Because you are changing the velocity. Okay, you are changing the state of motion. So if you go faster, if you go slower, you need to apply a force. Now, you can also turn. When you turn, you need a force, right? It's called a centripetal force. So it's not that you are going faster or slower. You can go at the same speed, but you are turning, right? But you need a force. And more inertia, harder it is to turn, right? More inertia, right? For the same force, you're going to make a larger curve, right? It's harder to take a turn for a truck than for a bike, obviously, because the truck has more inertia. So let me ask you something. If you have an elephant chasing you here on that campus because it escaped the zoo and it's running very, very fast, what should you do? Turn, very good. You have to go zigzag, because for you, it's going to be easier to change the direction of the velocity. But for it, it's going to be harder because it has so much inertia. So that's what they say. When there is something heavy going after you, you have to go zigzag, change the direction. Now, here, pop quiz question, typical tricky question. If you go to the moon, is the weight the same?
No.
But is the mass the same?
Yeah.
Yes. So inertia will be the same. So if you have something like an anvil here, very heavy, it's going to be as hard to push it on the moon that it is on Earth. It's going to be easier to lift on the moon because, of course, gravity is less. But when it comes to pushing on the ground, it's going to be as hard because on the moon it has the same mass. Okay? Oh, at what time did I put a pop quiz? I think it's 3 what?
325.
3:25. Okay. Okay, what about here? So you see you launch like a marble here, it goes zoom, 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 zoom. And so each time it's making a turn, that's because there is a force applied to it. If you want to make something turn, you need to apply a force. So the force is from you see here the wall here, right? The side of the tube. So what's going to happen next when there is no force acting on it? Straight, very good. It will keep going along a straight line at the same speed because there is no force acting on it. That's inertia.
Yeah.
So typical misconception, you don't need the force to keep moving. Right? You want to keep moving. That was not the idea of Aristotle. So it took like 2,000 years to prove Aristotle wrong. So which of the following term is used to indicate the natural tendency of an object to remain at rest or in motion at a constant speed along a straight line?
Inertia.
Inertia, very good, right? It's like the laziness. So someone in the back, can you turn on a little bit the light because people are falling asleep here? A little bit the light. You know there is like a slide. Thank you. Thank you. Okay, thank you. What's your name? Thank you. Okay, so that's humor, but I think it's not. I'm not sure if it's like that. This slide is very old, so I apologize. Times are not the same, so I don't know if we can make those joke anymore. So that was the first law of Newton. Second law of Newton, F equals ma. You already know that. As long as there is a net force, there will be an acceleration. How much acceleration you get depends, of course, on the mass. If you have a small mass, for the same force, you're going to have a huge acceleration. For the same force, if you have a huge mass, you're going to have a small acceleration. Okay, so what does that mean? It means that the acceleration is inversely proportional to the mass. Twice the mass, half the acceleration. 3 times the mass, acceleration is divided by 3. 10 times the mass is divided by 10. Okay? That's not too hard to understand. Inversely proportional. Okay? And for the same mass, okay, the acceleration is proportional to the acceleration. Sorry. Acceleration is proportional to the force for the same mass. So 3 times the force, 3 times the acceleration. Okay, so acceleration is proportional to the net force, inversely proportional to the mass. So for example, in an airplane, okay, so you are in an airplane here, and so of course, at takeoff, right, the airplane is gonna accelerate. So the airplane is not leaving you behind. So your body is also gonna accelerate. For your body to accelerate, you need a force. So the force will be provided by the chair you are sitting on. But someone with like an adult, for example, has more mass, so there will be a larger force pushing that person, so he can accelerate. If you have a kid, the kid has less mass or less force acting on the kid. So that's why in the airplane you see the kids, they are sitting, on their chair. They don't have to push their back on the chair, they're just sitting and they will be fine, because they have so small inertia that they don't need a large force to get them to the right acceleration. If you have a heavy person, for example, that would be very bad, right, to the stomach, because you need a huge force to get to that acceleration with a large mass. Does it make sense?
Yeah.
So when you say 1g, that means you're going to feel your own weight. When you feel 2g, that will mean twice your weight. 3g, 3 times your weight. So if the airplane has an acceleration of 0.5g, you're going to feel half your weight. So if you are 200 pounds, you're going to feel 100 pounds. But if you are 400 pounds, you're going to feel 200 pounds. Okay, because it depends on inertia. Does it make sense?
Mm-hmm.
Thank you. And that's it, right? Okay, so this unit is easier because it's more concept. And then by the way, it's gonna get easier, right? The hard